So thank you. My name is Elsa Teixeira. I'm a third-year PhD student at the School of Mathematics and Statistics in the University of Sheffield. And I'm going to talk about some work I did in collaboration with Karsten van den Broek, which is my supervisor, and Cameron Thomas, which is a fellow PhD student. And I'm going to start by introducing the standard model of cosmology in case you are not familiar with this, but if you are and this is boring, I have some nice illustrations so that hopefully I don't lose you until the end of the talk. And these are credits to my friend Inês Oliveira, and you can find more in this link. So to start, our standard model of cosmology assumes or is based on observational evidence that we have today for the accelerated expansion of the universe. So this was first detected in 1998, but today we have overwhelming observational evidence. So this comes from many sources. We can see this in the CMB. We can see this studying standard candles like supernovae or Cepheids, bow measurements. So we have a great observational support for this. So our standard model of cosmology is a lambda-CDM model, and it's based on three pieces of standard physics. So the first one is our theory of gravity, which we all know is general relativity. Then we have to specify a metric ansatz, and in this case we assume a homogeneous isotropic universe. So we assume Friedman, Lemaitre, Robertson, Walker metric. And then we also have standard matter, so baryons, photons, neutrinos, and everything we know of. And at the present, we know that this standard matter accounts to about only 5 or 6% of the total matter content of the universe. And the rest is actually in the form of some new physics, which we still cannot explain the true nature. So in the standard model, in the lambda-CDM model, this late time acceleration is explained by the cosmological constant, which is the lambda in the name. The cosmological constant is just a fluid with negative pressure, who basically just doesn't dilute with the expansion, so it's always constant. But this can also be explained with a scalar field with modified gravity. So it's, as I said, new physics, so it's still open to investigation. Then we have inflation, of which I think we will still hear a bit more about today. And this can also be explained by an inflaton shield or primordial gravitational waves or many other things. And then we have the matter that is responsible for the formation of structures so that we can have the cosmic web. In this case, in the lambda-CDM model, we assume this is CDM, so-called dark matter. But as we have just seen, this could be an axion or it could be other things like primordial black holes or anything. But the idea is that this is our standard model. It's theoretically very simple. It's based on just 6 free parameters that we fit to the data. And we know that it gives an impressive fit to measurements coming from the CMB and the large-scale structure, so large-scale distribution of galaxies. So here we have a picture of the Planck collaboration. So this would be in blue, the power spectrum, the temperature power spectrum as measured by the Planck collaboration, and the dots are the points measured by the Planck collaboration, and the curve would be the lambda-CDM prediction. So we can see that the curve gives a very good fit to the data points, and it's actually quite impressive, especially because the problems are all in the low scales in which we don't have a lot of measurements because of cosmic variance. However, even though this model gives very good predictions, we are now aware that it has some conceptual problems and mostly, or more concerning, some observational tensions. So here I'm going to focus on one of the most relevant tensions, which is the Hubble tension. The Hubble tension is just a problem that we find unreconcilable values for H0, so for the current expansion rate of the universe, when we use early time measurements, such as the CMB, so measurements of things that happen in the early universe and that then we have to propagate to the present, or when we use late time measurements related to objects that will be close by, so things like supernovae, Cepheids, these will all be late time measurements. And we see that there is a consistency between the early time measurements and the late time measurements, but there is a discrepancy between the two. So in particular, the most, let's say, relevant tension, or where we can see this better, is by comparing the Planck, because the Planck is a grand confirmation of the lambda-CDM model and is a very robust data set for which we predict an H0 of 67.4. And then we have the measures from supernovae, which are also very reliable, and from which we obtain a value of 74. So this is a 4.4 sigma tension, which is already considered a very significant tension. So since it's so large, it's also unlikely that the discrepancies could be explained by a single systematic error, also because all these collaborations make sure that everything is calibrated, and they also predict what kind of errors could be coming from, let's say, calibrations or model assumptions. So the hint is that there's probably something we are missing in the standard model if we keep seeing this trend of late and early measurements. So because of this, we now formulate extensions to the standard model, and then we try to test these extensions, especially against the model-dependent constraints, because those are the ones who will depend on the model and hopefully give us a different prediction. So we can do many things. We can vary neutrino effective number. We can have axion dark matter, as we saw, modified gravity models, so many things. And in this work, we consider non-vanishing curvature and interacting dark energy. So I'm going to explain how we do this. So one of the basic assumptions of the lambda CDM model is always that the universe is spatially flat. So this means that we take omega k, as we see here, to be 0, and it's not a free parameter of the model. However, if we see that if we add this as an extra parameter in the simulations, we get a non-zero prediction for the curvature. So this hints at a closed universe at more than 2 sigma. But what is found usually is that because this comes at the cost of having one additional parameter, is actually not statistically, it's not statistically relevant. In the end, we also get a lack of concordance with other observables, and in particular, this increases the H0 tension, but also alleviates other problems such as the sigma 8 tension, which I haven't mentioned, but it's another observational tension. And so the hope is to try and have the same, but without this problem. So we had the idea of considering interacting dark energy as well, hoping that maybe by having a flux of energy between dark matter and dark energy could give us a more accelerated expansion and hopefully greater value for H0 in concordance with the late time measurements. So the interacting dark energy, we take a scalar field, so a dynamical scalar field. In the canonical case, this is called quintessence. And what this means is that it's dynamical, so it evolves in space and time, as opposed to lambda, which is more always constant. So this gives us more flexibility, and we can more naturally fit the predictions. We know that dark energy cannot interact with normal matter because we have a lot of constraints coming from the solar system. So usually we just assume interactions with dark matter. So this will be represented like this. So we have, instead of our usual conservation relations, we will have an interaction term between dark matter and dark energy that might be positive or negative, and that will just represent an energy flow. And this energy flow could give rise to a change in the background and in the linear perturbations that could maybe at least alleviate the H0 tension. So, thank you. In the first approximation, we considered just a coupling being constant and proportional to dark matter and the simple potential. And we use Bayesian inference just to estimate our parameters in the theory. So we have the data sets. So we have the probability of the data sets. We have the probability of the data given our parameters, which is a likelihood. And we also have the priors on the parameters. So the information we know about the parameters. And then we can derive the posteriors. That is the probability of our parameters given the data. And then we just do an MCMC sampling analysis. And in this case, we consider just the Planck likelihood with a modified version of class and the multi-Python sampler, which you can find more information here. So again, we take the 6 free lambda CDM parameters, and then we add 3 more parameters for our interacting dark energy scenario, which are the coupling constant beta and the potential constant lambda and the curvature of the universe. So then these are just the preliminary results that we get from the data analysis just with Planck 2018 likelihood. So here in blue, you have the Schu's value for the H0 that you see is much higher than the lambda CDM. Then we have the lambda CDM flat value here, which we see is in tension with that one. And then what we see is that if we add curvature, we aggravate the tension. If we add interacting dark energy flat, we actually get a better fit to the data. But again, this comes at the cost of having more flexibility, so greater error bars and more parameters, so it's not preferred by the data. And then what we see is that when we add curvature to interacting dark energy, the tension is actually exacerbated. So it didn't solve the problem. But in the end, we see that there's still a preference for a closed universe. So we still get more than 2 sigma deviation from 0 for omega k. And in particular, we also find that interaction has the effect of bringing omega matter to smaller values. So you see here that omega matter is really high in lambda CDM when you consider curvature, and this would probably be a problem for comparing with large-scale structure distribution data, but for our case, it's smaller. So just to conclude, we saw that we have this lambda CDM model that gives an impressive fit to data such as the CMB. We saw that there's evidence for closed universe, but this gives us more tensions and other problems. So we assumed interacting dark energy, hoping to alleviate this. But we saw that this worsens the edge knot tension, but in the same way it gives better predictions for omega matter. So maybe by considering different couplings for scalar field potentials, we could have better results. So that's what we are looking at right now. So that's it. If you have any questions, I'll take them. And there's also here the reference for the illustrations again. Thank you.
Thank you. Might just have time for a quick question. Mm-hmm. Anyone wants to put anything in? Like, if I can jump in one with a quick one. You said that due to the extra complexity, the model wasn't preferred by the data. Did you calculate some Bayes factors between the different models? Is that something you can get from your MCMCs?
So from your MCMC, you can calculate actually 2 things. So you can calculate the Bayes factor if you already have good statistical confidence in your model, but you can also just calculate the minimum chi-square, and that's very easy to do given that you have the maximum value of the likelihood in your model, and that would already give you an idea. Or you can also calculate the DIC test, which will also give you an idea of how the model behaves in relation to lambda CDM. But usually 3 parameters, you would need a very big improvement in the fit to be able to say that it's statistically significant.
Cool.